Hello, Professor Malave. My name is Leonid Spanner, and our team, Isabella Oakes and Emmanuel Lukban, we're very excited to deliver to you our presentation on in-vehicle marketing engagement optimization.
Our dataset is titled In-Vehicle Coupon Recommendations and is located on the UCI Machine Learning repository. It was gathered from a survey on Amazon Mechanical Turk and consists of 12,684 data points, 25 features, and has a binary outcome of 1 meaning yes, a coupon was accepted by a driver, or 0 meaning that the coupon was rejected by the driver. The features of the dataset include the destination the driver was going to, the passengers in the vehicle, the weather, the temperature, the time, what type of establishment the coupon is for, how long the coupon is valid for, the gender of the driver, their age, their marital status, whether they have children, their education, occupation, and income, how often each month they go to bars, coffee houses, carry-away restaurants, restaurants that cost less than $20 a person, and restaurants that cost between $20 and $50 a person, whether the coupon's location is less than 15 minutes away, whether it is less than 25 minutes away, and whether the coupon's destination is in the same direction that the driver was going or the opposite direction. Most of the features had small to no correlation to the target outcome. The type of coupon did seem to have an effect on whether a coupon was accepted, with carryout and takeaway restaurants under $20 a person having a 70 to 75% acceptance rate versus bars, coffee houses, and restaurants costing $20 to $50 a person having around a 40 to 50% acceptance rate for coupons. The coupon location being farther away also had closer to a 40% acceptance rate versus it being less than 25 minutes away having a close to 60% acceptance rate. Most of the data in the dataset was complete with the features bar, coffee house, carry-away, restaurants less than $20, and restaurants between $20 and $50 missing between 107 and 217 values each. The feature car was missing the most values at 12,576 missing data points out of 12,684 total data points. To pre-process the data, we first dropped the feature car because of the missing data, as well as to coupon at least 5 minutes away as the responses were 100% yes, and the direction opposite feature as it contained the same information as the direction same feature. We converted the time to 24-hour time and expiration to hours. We changed the features bar, coffee house, carry-away, restaurant less than $20, restaurant $20 to $50, age, education, and income to ordinal values. The features destination, passenger, weather, coupon, marital status, and occupation were transformed using one-hot encoding. Finally, we transformed the Gaussian features using standard scaling, and the non-Gaussian features were normalized. We then assigned the target to a new data frame named labels and split the data into a 75-25 train test split.
We use the generalized logistic regression model to establish a baseline accuracy score, but more importantly, to bridge the gap between our exploratory data analysis and predictive analytics. In so doing, we rely on the descriptive form of the logistic regression model as follows. This breaks down to predicting coupons in the following equation. We take into account the average income, education, and begin our feature selection process. Based on the summary output table, our current feature selection shows that whether or not an individual has children bears no statistical significance for this baseline model at a p-value of 0.107, and thus we omit this predictor from this model. That being said, we will explore reintroducing this variable for subsequent models. Moreover, in the confusion matrix, the 1,178 true positives indicate that this many people are interested in receiving coupons given the current feature selected. This produces a baseline accuracy of 59%. Once our preprocessing is complete, including all of the relevant feature selections, we begin to tune our hyperparameters to see if we can improve our accuracy score from the baseline. In so doing, we tune the logistic regression model over a list of different cost values, for which we apply a default L2 norm penalty to pair with the LBFGS solver. This is also known as the limited memory Broyden-Fletcher-Goldfarb-Shano. It uses gradient evaluations to approximate the second derivative matrix updates. We then set our max iterations to 2000 so that the model does not fail to converge and include the cost hyperparameter. Moreover, the results show that the optimal test accuracy of 69% is contained within the cost hyperparameters between 0.1 and 1. We then plot our test accuracy and training accuracy on the same plot and show the confusion matrix where 1,396 true positives indicate that this many people are interested in receiving coupons given the current features selected. One of the most important reasons for creating a decision tree is to trace the consumer's path to accepting and or rejecting a coupon recommendation. An untuned decision tree can take us down an endless road of decisionless consequences. Therefore, we tune our max depth over a relatively broad range to give us a sense of the optimal hyperparameter given the highest test accuracy. Though a max depth of 10 provides the greatest test accuracy of 70%, we don't necessarily want to see a decision tree with a max depth of 10 because it will prove to be quite complex and hard for us to decipher. So we choose a lower max depth of 3 so that we can follow the decision tree with relative ease. From our ensuing decision tree, we can assert that passengers with kids are less likely to accept coupon recommendations for carryout and takeaway orders, whereas those who open the coupons within a proximity of 20 minutes to a restaurant and those in and around a coffee house are more likely to accept the coupon recommendations. We next rely on the highly flexible modeling techniques of support vector machines for our classification endeavor. Once again, we tune the model over a set of cost hyperparameters and use the radial basis function kernel with an automatic gamma. Gamma measures the extent of a single training example. Since our data is not easily linearly separable, we rely on the radial basis function kernel to solve this problem. This is where the Euclidean norm of vector x minus x prime squared is the Euclidean distance between the two feature vectors, and gamma is equal to 1 over 2 standard deviations squared. Simplifying the equation, we have the following. Increasing the cost at every step penalizes the model, but produces a greater propensity for classification at each iteration. Thus, our highest accuracy of 76% is achieved where cost equals 50. Optimal testing accuracy along training accuracy is depicted in the following graph. Moreover, in the confusion matrix, the 1,467 true positives indicate that this many people are interested in receiving coupons. As part of our modeling process, we examine k-nearest neighbors through the lens of Euclidean and Manhattan distances, respectively, varying the number of neighbors at each iteration.
The first k-nearest neighbors model that we use is the Euclidean distance model, which is defined as the square root of the sum of x sub I minus y sub I squared. We then tuned the model over 1 to 19 neighbors using odd values and found that setting the model to 5 nearest neighbors gave us the best accuracy with the simplest model, with 0.67 for test accuracy and 0.78 for training accuracy. The recall for this model was 0.78.
The distance between 2 points x and y is equal to the sum of the absolute value of x sub I minus y sub I from I equals 1 to n. We select odd numbers, namely 1, 5, 11, 15, 21, 25, and 31 as the number of neighbors to loop over, and consequently find that the optimal test accuracy exists when the number of neighbors is 31. And that gives us a test accuracy of 69%.
The random forest model was tuned over max depths from 1 to 20. The max depth at 19 had the highest test accuracy with the simplest model. The area under the curve for the tuned model was 0.74 with accuracy at 0.76, recall of 0.84, and an F1 score of 0.79. The naive Bayes model has an area under the curve of 0.71, accuracy at 0.62, recall of 0.65, and an F1 score of 0.66.
To model the complex linear and nonlinear relationships that may exist in the data, a fully connected neural network was trained and tested. After extensive training and tuning of the hyperparameters, the optimized model consists of 6 layers, 124 hidden units, and rectified linear units for activation. During training, the model is prone to overfitting, and dropout was used to reduce the model's overall variance. The tuned model outperformed a baseline model with an overall accuracy of 71%, a recall of 79%, and an F1 score of 76%. In addition to naive Bayes, Gaussian discriminant analysis was tested as another generative approach. 2 models were trained, a QDA model, which generates quadratic decision boundaries, and a simpler LDA model, which will generate linear decision boundaries. Both the QDA and LDA models have no tunable hyperparameters. Both QDA and LDA outperformed the baseline model with accuracies of 67% and 69% respectively. The QDA model has a recall of 69% and F1 score of 70%. The LDA model fared better with a recall of 79% and F1 score of 74%. Gradient boosting model, like random forest, is another ensemble of decision trees. Unlike random forest, however, gradient boosting models construct trees sequentially, with results being improved at each iteration. Tuning of the gradient boosting model was similar to the random forest, evaluating training and test data accuracy over the number of generated trees and maximum depth of each tree. As you can see with the graphs, the optimal gradient boosting model has 500 trees with a maximum depth of 15. The gradient boosting model outperformed the baseline model with an accuracy of 76%, recall of 83%, and F1 score of 80%. The gradient boosting model performance is similar to that of the random forest model and producing comparable metrics. However, the gradient boosting model achieved a higher F1 score and area under the ROC curve. In conclusion, based on the survey data, a naive approach of a non-targeted blanket distribution of coupons will only be accepted by 57% of the population. Leveraging data to model the relationships between the various demographic and environmental variables that contribute to the audience's receptiveness can increase engagement rates using a more targeted approach. Using predictive models also allows for simultaneous targeted promotions through audience segmentation. Sending promotional offers that are predicted to be the most receptive to each segment instead of bombarding each user with multiple promotions that may not be desirable or appropriate. The top 2 performing models are gradient boosting and random forest. The model's predictive performance and test data are strikingly similar, both with an overall accuracy of 76%. However, due to the nature of the project, true positive rates take precedence over accuracy, since false negatives will lead to an opportunity cost. Therefore, the key metrics for model selection will be recall, F1 score, and area under the ROC curve. Although the random forest model scored 1% higher in recall over the gradient boosting model, the gradient boosting model scored higher on the F1 score and has a larger ROC AUC, suggesting a significantly lower incidence of false positives. Gradient boosting also has more tunable parameters than random forest and may have more potential for improved performance. Therefore, we conclude that gradient boosting model is the appropriate model for this project.
Thank you for listening to our presentation.
From Team 2, thank you all for attending our presentation.
On behalf of Team 2, thank you for your time, and this concludes our presentation.